All right. Welcome to Electronic Control Systems. Um, uh, Probably this is first course to some of you, and some may have already done it in undergrad. Therefore, we are pitching somewhere in between. But I have realized over the years that if you have been away from academia for 4 years, maybe you need to get your foot on the contents first, get the grip is extremely important. So therefore, most of the time I will stick to the basics, but trying to pitch high at different sections, right? The reference book is Classical Control Systems, ISBN, this number. I think the book is available at the university bookshop. This is my own book, particularly designed for the first course in control systems, from modeling to controller implementation. Because I have realized most of the reference books like Gupta, Lewis, Franklin, etc., too big to be covered in one semester. Some have like 400 plus pages, very big books. So thought of combining the contents together and line them up properly without spending too much time on any of the sections, and try to help students to walk faster from start to end without spending too much time in each of the sections, right? Having said that, it's also important to have the depth when you learn, but depth is a relative thing, and you can go, depending on your time availability, certain depths in control systems. Okay, so what is most important for a control system engineer is to know the entire workflow from A to Z without spending too much time on A or B or C or D, not being able to walk to the end of the line. Okay, so that is the whole purpose of this course. Some of the lecture notes I will be giving you, so you don't need, it's not compulsory to buy the book. If you buy, it is very handy, not a regular size book, maybe a bit smaller, right? I think 1/8 size or so. It will be handy, but it's not a must because the notes are provided, lecture slides, they contain pretty much the same thing. Number two, MATLAB. So this course is heavily dependent on MATLAB, because it's very nature of control systems, right? It can easily go out of your hand. Okay, so you need to have some sort of platform, right? So that you can code it and see for yourself what the actual responses are, the behavior of the plants, tune gains, tune design controllers, right? You can't have everything like realized in your mind. In that case, different people will understand it in different ways. Okay, that's very dangerous. Sometimes you might misunderstand and you keep it with you. MATLAB is very easy for you to visualize some of the contents that are difficult to understand, or not understand, particularly to visualize. Okay, so I mean, I'm referring to two things here. One is the theory. You need to understand, and then to quantify it. When you do control systems, very much a practice of quantifying things. When I say there's a plant and you need to control this plant to a certain level, let's say it's a air conditioner and you want to set the temperature to 26. Okay, so if it is say now 29, so you want to see graphically how this 29 goes to 26, how long it it takes, and whether it goes straight or whether it goes a little slower first and then faster, converge at 26. There are various ways of getting there. So if you don't have a visualization platform like MATLAB, you will not understand it fully. Okay. So I need you to download and install MATLAB, right, on your laptops and get going with MATLAB. So when you download, probably you can get a free student version for some time, and there are other torrents, etc. If you want, right? I'm not going to help you in that. You can find it out yourself. It's essential for a number of reasons. One, of course, to understand the theory and practice, become an engineer, expert in control systems. You need this platform. Number two, you need it for final exam also, because in the exam I'm going to ask you to code certain design problems in MATLAB, and then you have to verify it by running it on your laptop and get the results, and then you have to copy it from your laptop screen to the answer book. Okay, so you have to write your code, verified code, and also the result. So therefore, for multiple reasons, you need to have MATLAB. So do it sooner the better. Okay. All right. So having said that, let's move on. What you see here is the content lineup. These are the contents we're going to cover in this semester, right? First, we're going to look at the historical control systems, how people started with control system design. Okay, it's a long story, very old. We are going to even BC era, before Christ. So I'll show you some of these classical stuff. Number two, mathematical modeling of plants and systems. As you know, if you want to design a controller for a plant, you first need to model the plant. We need to have some equations, differential equations, that is characteristic to the plant. So using the differential equations, we understand how the plant behaves. Okay, so mathematical modeling is extremely important. It is the stepping stone, the first step of any control system design. Okay, so right over here I have written what it is. What I really mean by that: input-output relationship as an ordinary differential equation. So if you look at a plant, it's an input-output entity. It has input port and output response. When you give an input, a signal from the input port, you get a response. Okay, if you can write an equation, let's say x and y, for example, x is the input, y is the output. So if you can find out y as a function of x, this is all what I mean here, mathematical modeling. Okay, so this way, if you know, okay, if you give a certain x, you get a certain y. And if you do it the other way around, I want y to be at a certain value, let's say 26 degrees. Okay, and in order for y to go from, say, current 29 to desired 26, how should I control my x? All right, so if I have this relationship, I can do something about it, right? Try to adjust x gradually, right? You can't just keep one value indefinitely and expect y to change from 29 to 26. So you need to have some sort of gradual change in x also, so that the y will change in a desirable manner. So to do all these things, we need to have a mathematical model of the plant. So we're going to look at that initially. Number three, determining the response of the plant and system. We're going to look at in detail the characteristics of the response of the plants, right? Some plants are, we say, stable, which means it goes to a certain value in the response and stay there. And some plants, they always go up and down, like oscillating, right? They never stabilize. I mean, it's another mode of stability. It's not unstable, right? But it doesn't converge to a certain level. It's ever oscillating, going up and down like that, simple harmonic motion. And then you can have some system totally unstable, which means the response goes like that, right? And you know, anything, if it continues to rise or drop, it's unstable, which means it's gonna hurt somebody, something, sometime, right? So that's unstable systems. Say, for example, it's a temperature control system. If the temperature goes indefinitely high, at some point of time, something will burn, okay? Something will catch fire. So that's the end of the story. So we want to look at the response and then comment whether the plant is stable or unstable, right? Or what. So for that, we're going to look at what is called poles. In plants, there are something called poles, right? We'll get into that later. But initially, I want to tell you, it's like a story, right? In any plant, there's what's called poles. Looking at the poles, we can figure out we can get some idea of how the response is going to be, right? Because the response and the poles are related to each other. In other words, response comes directly from the poles, okay? And also we're going to do some simulation in MATLAB and verify the performance, right? That's why MATLAB is extremely important. Number 4, design a feedback control system. Then we are going to design a feedback control system, right? Feedback means you first look at what the response is, the output is, and if it is not what you want the response be at that moment of time, right? Then you want to adjust your input control signal, right, in that right direction, so that in the next few minutes or few hours, the response will change in a desirable manner, okay? So that is the design of feedback control system. There are a number of ways. We're going to look at that later. Number 5, frequency domain analysis of control systems. Right. Now, if you look at a plant, it's like a filter, which means it has an input, it has an output. So whatever goes from into the system through the input comes out as the response from the output. You can describe a plant like that, input output. Now, input signal, you know, Fourier series, Fourier transforms, which means any time signal can be broken down into its frequency components, right? Any signal. Then you can figure out what is the lowest frequency in the signal, what is the highest frequency in the signal. So it's a band, okay? The bandwidth of the signal. If you look at the response, output side, again, you can see what is the lowest frequency there, what is the highest frequency there. So there's another bandwidth there. Then you can figure out whether these two frequency bands are the same or different. Then you will understand that some of the frequencies, when they pass from input to the output, right, attenuate. Their strength goes down, okay? That is what is called the attenuation. That is why I said plants are like filters, okay? So we're going to look at that. If a certain plant attenuates frequencies in a significant manner, which means if you go to the response and see, you will see only low frequencies there, low frequencies there. So that is inherently slow system, inherently slow system. But if you see a plant where the output has high frequencies, so it's a high bandwidth system and a fast system, okay? So agile, fast, quick means high frequency, okay? If you see somebody very fast, very quick, very agile, you can say this guy has a high bandwidth, okay? And if you see someone else always slow, very like slow in attending to anything, then he's more stable than the other guy, but it's low bandwidth. Okay, sometimes we need low bandwidth, sometimes we need high bandwidth, depending on the plant. Right? We can't say low bandwidth is not good, high bandwidth is good. No, not the other way as well. Right? Depending on the requirement, we need to adjust the bandwidth. So therefore, it is important for us to know what is happening to the frequencies that are going from input side to the output. Okay, we do this in a body analysis. We'll do that later. Then PID, you may have already heard that word PID, proportional integral and derivative, is the most famous industrial controller. We will see how we can develop a PID controller for a plant. Okay. And then once you do all these things on paper or on your computer using MATLAB, right, that is not enough, right? You want to implement it in the real plant. Let's say the machine is in the factory floor, machine shop, right? And your controller is on your laptop, right? That's not the end of the story, right? You have to bring this controller and synthesize it in some way as an electronic device, and then you plug it into the plant. You're not going to plug your computer to the machine, right? So we'll see how we can design and build the control electronically. There are two ways to do that. One is analog. You design your controller, or you realize the controller that you design on MATLAB using analog components like op-amps, RLC components, right? And then you can plug it into the machine and it will control the machine. Or else you can have digital control, which means, PIC microcontrollers, Arduino, Raspberry Pi, STM boards, that kind of digital embedded platforms. So you can bring this code, MATLAB code, and convert it into C, or you can directly program any of these embedded platforms by connecting it to the your laptop and using the API, application development environment, and then code it and then flash the code right into the embedded platform, and then you hook it up to the machine and it will control the machine. Okay, so that is the lineup of this course. And I'll be giving you some tutorials on the way, maybe maximum 5, okay, not more than that. And if you fail to submit, all of these courseworks will be on Moodle. You don't email your answers to me, right? Every assignment is given a week to complete. They are not very big assignments, and there's a deadline on Moodle. You have to upload your answer script to the Moodle, and it's an automatic thing. If you miss a minute or second, you are unable to upload. Okay, so therefore, when you upload your answer scripts to the Moodle, let's say the deadline is tonight, midnight. Okay, you better make sure that you upload it about an hour or two before that, right? Not to have last minute surprises, because if you come up and tell me, okay, you had the answer script, but by the time you try to upload, you had a power cut and you were unable to upload, I can't help you in that respect, right? So that is why I give you enough and more time to answer your assignments and then upload it well in advance. Okay, so for exams and assignments, we are not taking power cuts as an excuse, because we simply can't do that. Everybody is having this problem. So therefore, we can't accept it as an excuse. And if we do, things will turn into chaos. Okay, we won't be able to implement this program in the first place. So therefore, when I set the deadlines, right, usually for assignment 1 week, for something more than that, sometimes 2 weeks, I go like that. Once we set the deadline, right? It doesn't mean that you have the entire time to you because of the power cuts and all that. You better complete or submission, whatever, well in advance. Okay, right. That is how we go about it. Any questions? Any questions about the management, course management, not the technical content? All right. So let me start with the first one, historical control systems, feedback by design. So good old days, right? People developed uh, control systems, right? Without any of these design platforms, sometimes not knowing the theory behind. They were like some of our crude inventors who actually put things together and create something, an apparatus. Very much so, right? That is how any field is developed, right? What you see over here is 250 BC, so that old, right? Flow regulated water clock. This is a water clock basically, because as you know, one of the very first needs of the humankind is measuring time. Measuring time. That is one of the very first thing. It's not any other thing, right? Just measuring time. Particularly the historical stories say in courts in Rome back then, right? They needed to have an apparatus to measure time, because when you hear a case, you have to give equal time to both parties, right? So you need to have a clock. So this was invented by Setibus, a Greek inventor. If you look at how it works, right, it's a fantastic concept. Now there is this funnel kind of thing, and there's a water inlet. Water comes into the funnel, right? And then it goes down to through the drain pipe into this container, right? And there's a outlet also here. If there's any excess water, that will go through this B, which means you cannot raise this water level beyond this point. No matter how hard you pump in, the excess water will flow out of the funnel through this outlet B. Okay. So when you maintain this height as a constant, right, then you have the constant pressure over here. When the pressure is constant, the flow rate is also constant. So you are getting water to this cylinder at a constant rate. Okay, so that is the heart of the invention. How can you have a regulated water flow? Regulated water flow, as the name says, flow regulated. It's a regulated flow. The flow rate doesn't change because the height doesn't change. So when you get a constant rate, water at constant rate into the cylinder, this piston kind of thing, a float, will go up. If the water level goes down, it goes down as well. But here what we do is going up only. Okay. So when it goes up, the height is proportional to the volume. Volume is flow rate times time. When the flow rate is constant, is proportional to the time. So that is simply the equation. The whole story is in one equation here. Height is volume over area. Volume is flow rate times time over area. Flow rate is constant. Area is a constant. So then it's K times T. Height is proportional to time. That's it. So then you can convert this into this rack and pinion mechanism, then have a needle, and you get the tire. So that is one of the very first working water clocks in the world, right? Now our focus is not actually the clock. It is this flow regulated thing over here. The core of the invention is just this. You can see this container, this is the outflow, this is the inflow. Water comes into this container, and it is fully sealed kind of thing. Maybe there are some air holes for the air to go in and out. And then there's a float of this shape. It's a three-dimensional thing, okay? So when you get more water into the container, this float this is a guided float, okay? It can't go here and there, right? It's a guided thing. The sharp edge is actually pointing upwards into this inflow. So it will move up and close the opening here. Okay, when you get enough water, this is what happens. And then it will cut down the water flow into the container at that point, at that level. So then, because of the outflow, the level goes down. The float will go down, and the moment it slips down a little bit, it will open this opening and get more water. So as you get water outside the canister, the container, you help it to get more water into the canister. So therefore, eventually there will be little fluctuation over here, but it will stay very close to this point, right? And whatever water goes out is equal to whatever water comes in. So when the two flow rates are equal, that will happen at that point. We call it trimming. You can trim your system when the float is at the highest possible point, almost closing the inflow. Okay. So when that happens, you get an equilibrium point. It's not a static equilibrium point, it's a dynamic equilibrium point, which means there's water coming in and there's water going out. They're both equal. The two flow rates are equal, and this float will stay there without going up or down. Okay, if it goes up, you don't have the equilibrium, which means inflow and outflow will be different to each other. Okay, there's a certain position of the float valve here, the float, where you get inflow equals to outflow, then the water level will not change. When the water level is constant, outflow is constant, right? So when you get to that situation, the state, we call it a trimmed state, trimming. Okay, trimming in control system is a very common thing, trimming. Okay, we'll look at that maybe a little later. In MATLAB also you can trim your plant, right? Any complex plant, if you cannot manually trim it, MATLAB will help you, provides a platform to design your complicated control system, and then say, okay, you want the plant to operate like this, you want to have this equilibrium of the plant, and you set some of the signals to that level, then MATLAB will run a code and figure out, okay, if you want to achieve that equilibrium state, these are the values of the signals you have to set. Okay, right. The second thing I want to show you is this one. Yet another invention by Phryllon, again a Greek inventor, 200 BC, 50 years or half a century later than Setibus. So what is this one? This is like more close to us. It's a oil lamp. Okay. Now it's a very special arrangement of oil. You have oil bath here, and from the oil bath you get some oil over to the lamp, and this is the wick and the flame. Okay, And there's another canister here to which you can fill oil. So oil, there's huge amount of oil here. Okay. So as the flame consumes oil, this oil level in bath B drops. So maybe it's easy to explain the whole story over here in this diagram, right? So this is bath B, and there, as you consume oil, the level drops. When the level drops, there's an opening over here. There's opening over here. The air goes into this tube and pressurize this chamber N, this one. So when you get more air into this one, because of this pressure here, it will push some of the oil through the drain channel here back to B. So B gets more oil. Okay, B gets more oil. And then when B gets more oil, this water oil level goes up and closes this tube, and no more air will go into the chamber M and N here. Okay. See how the system is so well connected. So it goes on by itself. You don't have to do anything. The system is stable. Signals are interacting each other and they adjust themselves. Everything is stable. Okay. As long as there's oil here, right, you can fill just the right amount to be, you are not overflowing this one, right? That is very important. You keep the water level, oil level here without actually pumping all oil over here so that you spill it over. Okay, no, it doesn't happen. You keep that amount there and remaining oil is here. As and when necessary, only you get that oil into bath B. And everything happens naturally. So this is the feedback basically, right? Feedback means when B wants more oil, it has to communicate it back to the main reservoir. There should be some way of communicating. Right now, in the present day, we deliberately do that. We communicate and ask more. Here, there's no communication, right? It's a physical design. So that is why I title it feedback by design. This feedback communication is embedded into the design, right? Without having a separate communication line, is part of the design itself. Let me show you another one, because these are all very interesting. These concepts, I think grabbing the concepts here is very important for a control system engineer. Okay, because this is the core, this is the spirit of the subject. Okay, if you don't have that spirit, you will find it difficult to make progress, right, in the subject. It's like if you want to be a good singer, right, it has to be in your genes, right, at least to some extent. Rest you can develop by practice, by spending more time, more resources, right? You can further develop it, but you need to have something in you, right? Maybe by birth, I don't know. So here also this alignment to the subject, this natural resonance with the design here, right? If you can capture that skill, right, you will be better off. Then whatever comes, the mathematics, MATLAB, whatever it is, all are actually peripheral resources for you to further develop yourself, right? So even without any of these things, without no MATLAB, no equations, people have developed these things because they had the instincts to do that, right? So what is this? This comes from 1st century AD. weight regulated liquid filling device. In fact, this was first demonstrated in pubs in Rome, right, for the soldiers, right. They used to flock around in pubs and drink wine. So this is actually a wine jar. It's a big wine jar, right? And before this, it was like the bartender was there and soldiers went and they would request wine, then the bartender would give them, right, wine. So that's it. Now there's no bartender now, there's a device. So soldiers go there and they just put the cup here, empty cup, and naturally they get wine to a certain level, and when the cup is filled to that level, you don't get any more wine, just stop naturally. So it was like a miraculous thing back then. And the records say the soldiers were so fascinated about it, and they kept putting the cups in that place over here, right? Just to verify whether it stops every time, right? Again and again and again. So what happens here is this: when you put the cup here, initially it doesn't have any wine in it, so it's lightweight. Because this is lightweight, if you look at this cross arm over here, this swings upward or anti-clockwise, this direction, right? Empty, when the cup is empty. So when this cross arm swings like that, this arm goes down when it is empty cup. So when this arm goes down, it is hinged here. So this side goes up. So when this side goes up, it opens the valve here. This is a valve, right? So this stick goes up and there's opening here. Some of this wine will go through this drain line again to the cup. That's how how wine gets into the cup, empty cup. Now when the cup gets more and more wine, it becomes heavier, and this is trimmed in that state, right? State of operation. When you get that amount of wine, this will be heavier and it will swing clockwise now, clockwise. Then this goes up, this goes down, and you close it. Okay. Then you don't get any more wine. When the cup has some amount of wine, it's heavy enough, and it closes the valve. So simple mechanism. The last thing in the lineup is this one, James Watt 1788 fly ball governor. I think this is the most recent thing. Fantastic invention, right? To regulate speed in locomotives and other machinery. Okay, during that time, mining industry and also the railroads were built, and they need to have these carriages in different mining industries. They wanted to have these carriages to have same speed, right? To bring graphite and other minerals from the tunnels, right? And also locomotives, steam engines, you need to maintain a certain speed, right? You know, in the first steam engine designs, when they fire coal, you get that heat to generate steam, and the steam goes into the engine, and you get the piston motion. So if you cannot regulate the steam, you are in trouble. Then you cannot regulate the speed of the locomotive, right? The whole purpose of the locomotive is to maintain the speed at the same speed, right? You can increase it, decrease it, but most of the time it goes at the same speed. So this is the device to self-regulate the steam flow into the engines. And you can easily understand it. Now, this is the steam engine. This is the steam line through which you get the steam. And this is the steam generator. Maybe you fire coal here, right? Water container, and then it generates steam, right? And then you get the steam into this one, right? Just early this year, I went on a steam engine. Fantastic experience. Very old design. They're keeping the same engine for more than a century or a couple of centuries now, right? That was a great experience. So what happens is this. This is the invention. This was what was invented by probably James Watt, and there are stories. Not only James Watt, there were a few other people working on the same thing, right? And they also were inventors. So somehow or the other, we only remember mostly James Watt. Okay. The steam engine has a rotary thing because everything is rotary, right? Actuators. So you couple the engine rotation into this one, right? So this is the rotary thing. As the engine rotates, this thing also rotates. It's like a sensor, basically. So there are two steel balls, right? When you rotate faster, because of the centrifugal force, these two steel balls, they fly away, right? They fly away as you increase the speed. As the engine speed increases, these two steel balls, they move apart, right? They move apart. So if you look at this mechanism, when the two steel balls move apart, this point comes down. See this mechanism, right? This point comes down. This is the hinge point, and this point goes up. Now you see how this link is connected to the valve here. So when this guy goes up, you close the valve. You close the valve here. When you close the valve here, you reduce the steam flow into the engine. When you get lower steam flow into the engine, naturally the engine slows down. If it slows down beyond a certain level, too slow, right? Then again you can see when it is spinning slowly, the steel balls come closer to each other. When that happens, this side goes up, this side goes down. When it goes down, you open the valve a little bit, letting more steam into the engine. So this happens naturally. All what you need to do, what had to do is to trim the system. Trim means at what speed you get just the right amount of steam to maintain the desired speed. Okay, you have to start with that. What is the desired speed? And at that point, what is the steam flow you want to get? Right? That particular steam flow gives you that desired speed. And at that point, you design this part so that a certain amount of weight and the distance and everything you calculate to that state of motion. And at that point, you calculate this lever and everything and tune it up and tight it up with that particular opening here. Okay. If you keep it more, which means you get more steam, then it will stabilize at another speed, which is too fast maybe, right? So this is all what is called trimming a plant. This particular plant, you want to maintain the steam flow rate which gives you the desired speed. And if it changes from that state, it has to self-regulate itself. Okay, if the speed of the engine here is, let's say, 50 kilometers an hour. So when it is running at 50 kilometers an hour, you get certain amount of flow rate, steam, and it is just enough to maintain 50 kilometers an hour. For whatever reason, maybe now the train is going uphill, so it slows down. It slows down. The moment it slows down, the steel balls come closer to each other, right? Pushing this up, pushing this down, and you get little more steam. Now you are getting more steam to gain that speed that you lost because of the uphill climb. Okay. Similarly, if you go downhill, coming from, let's say, Kandy to Colombo, then you naturally speed up. So you are in trouble now, right? Naturally speed up. Then if you apply brakes, that's a separate thing. But before that, this mechanism also provides some sort of speed reduction. How? When it slows down again, steel balls come closer to each other, right? Pushing this down, right? And pushing this, the other way. So if it is slow speed, they are swinging at a slow RPM, right? And the steel balls rather, come together, push this up. This side goes down, and you open it up, get little more steam. Okay, that is basically uphill one. Downhill one is when you speed it up, high speed. When you have high speed, you are swinging the steel balls away from each other too much, and then you bring this guy down, and this goes up and cut it off. Okay, so this is a fantastic device, feedback again by design, and that was one of the major inventions back then in 18th century. All right, so the purpose of showing you these inventions is to inspire you about some of the historical inventions people made, even without any development platforms, software, hardware, whatever, right? Very crude hardware, but they had the instincts. They knew the feedback concept, and they built those devices. So now we start the formal discussion on mathematical modeling of plants and systems. Okay, so we are not going to do the way the Phelan did, Sativus did, then James Watt did, right? So I don't know whether they really did mathematical modeling. I doubt very much. Now, if you are given a problem, you have to do it in a different way. State of the art process. First step is mathematical modeling. So to show you how we do it today, I wanted to look at this example, something which is familiar to everybody: shock absorber, right? Motorcycle shock absorber. See this one. So let's say this is the plant, right? This is the plant, the system, and we want to mathematically describe it. Okay. So how do I do that? I first draw the components. We call this white box thing. You know, white box. White box means there's a box and there are certain things in it, You can shine a light into the box and you can identify all of the components. So it's what's called white box. On the other hand, you have what is called a black box. I think familiar to you. Black box means you don't know what's inside. Right? You can see what's going into the box and what's coming out of the box, but you do not know what is in the box. So this one is white box. The white box problem. You have the spring. So we draw it like this. This is a spring. And inside that, you have what is called a damper. What's called damper. Damper is something like that. You can see it over here. If you push it from here, it doesn't just simply go down because of the sealed container here. There's oil on either side of the piston. So this oil has to come from this side to that side. It's not easy, right? Oil is viscous and there are small holes through this piston kind of thing. You have to give time for oil to come through these holes from this side to that side. So it's a controlled motion. No matter how hard you try, this guy moves in a particular manner. So we call it damper. Okay. So you have the spring, you have the damper. And then this side is connected to the axle of the wheel, and the other side is connected to the seat and the rider. So this is very familiar to everybody. So I thought of discussing this particular device so that you can understand it. Why we have this shock absorber is roads are not very flat. Right? Roads have irregularities. This is not the reality, the flat ground. There's always irregularities. So as you ride your bicycle, the wheel follows the terrain. Every little irregularity on the ground, the wheel has to go through this up and down, right, motion. And if that up and down motion comes to you as the rider, it will be very uncomfortable. Okay, you want to have a comfortable ride. As you move, you want to maintain a certain a nice curve, right? Somewhat parallel to the road, but without any small vibrations, right? So even if you go over a small pit on the road, you should not feel the whole change of motion, right? If you have this kind of thing. The device here, the spring and the damper, will absorb the shocks, right? The vibrations, right? Not letting that vibration to come to you as the rider. Now, once you draw the diagram, we call it free body diagram. You identify the components, spring, the damper, the mass, and then you draw the forces applied here. So there's a force from the spring and there's a force from the damper. Okay. You have to write down the mathematical equations for the forces. As you know, spring, if you squeeze it by a certain amount, it resists the motion, right? The force rather, by this equation, K times Yt. So Yt is the motion, right? Yt is the motion. If you try to squeeze it or stretch it, either way, it will provide you an opposing force equal to this amount, K times Yt. So Y is from the trim point, right? Any deviation, up or down, up or down. If the seat moves down a little bit, there's an upward force, or if the seat goes up, it's a downward force. This is pushing or pulling, right? And if you look at the damper, the equation is B y dot t. It's again this y displacement, but it's not just y dot. Rate of change of y. Rate of change of y. So if you move at a certain speed vertically, right, proportional to that speed, there's opposing force from the damper. So these two guys are too different in responding to the force Ft. Ft is the force coming from outside. Can be due to vibration or anything else. For this, whatever force, right, which causes the deflection here, motion and the speed, okay, the displacement and the speed. Spring produces a force proportional to the displacement, and the damper produces a force proportional to the speed. Okay, right. So that's the second part of the process, mathematical modeling, to draw the free body diagram of the plant. Next step is to write down the equation of motion. Okay. Look at the forces applied here. So there's a force applied. Let's say this is the rider's mass, this M and the body mass and everything, right, together as the mass. Okay. So the weight. So we'll reflect that as Ft. Ft is the force. Okay. Can be weight of the rider. So that is one force. There are two more forces. The other one is from the spring and the other one is from the damper. So we can write the vertical force Ft minus the downward force Ft minus upward force Kyt minus the upward force By dot T. Okay. Is the resultant force. Is the resultant force either downward or upward? We don't know. Whatever it is, if there's an imbalanced force on a body, mass M, it has to accelerate in that direction. So we call it My double dot T. My double dot T. Mass times acceleration. So this 2.1 is the equation of motion. Now these two parameters, K is the spring constant, how many newtons per centimeter, and B is the damper coefficient, B, how many newtons per unit speed, meters per second, okay, or centimeters per second, whatever it is. So then what you do is you arrange this equation in this particular order. The first term is the highest derivative, and then the next one, finally the variable itself. The variable here is yt. On the right hand side is the external force. External force is F. So you bring it to the right hand side, or it's already there. You bring the other terms, y related terms, yt and y dot t, to the left hand side and form this equation. And also you divide every term by simple m, so that the first or highest derivative has its coefficient as 1. Okay. And if you look at this one, 2.2, this is the mathematical model of the plant. Mathematical model of the plant. If you know the spring constant K and the damper coefficient B, right, and also the mass, right, these are the parameters of the model. And then if you give any Ft, any force, okay, you can simulate this mathematical model starting with some y and y dot t. Initially, what was yt? What was y dot t? And then you can calculate what is y double dot t. What is the rate of change, acceleration. So once you have the acceleration, you can predict the next position and next velocity. And these things are not going to change. And then you can update y double dot t. So likewise, this will go on and on and on for a particular force. Right? This mathematical model will explain you how y double dot changes every moment. Okay. The moment you have this force, there's a huge y double dot t. But as this spring squeezes and the damper resists that motion, y double dot will not be that big. So gradually y double dot will go down to 0. And so is y dot t. That will also go down and settle at 0. So when y dot t is 0, which means no motion. And then there is some yt, which is different from now, right? It's another equilibrium point. So that is what happens when you jump onto the seat of a motorcycle. It will squeeze a little bit and then settle. So if another person jumps in, 2 people, the seat will squeeze further and settle down at another point. Okay. So from start to the end, how the signals change is described by this dynamic model. It goes to the second order derivative, y double dot. Start with acceleration and then velocity and then position. Okay. So now you understand how important it is to model a system so that we can understand how it behaves. Okay, what it is there in the system, and if you disturb the plant by giving an input or control signal, how the system respond to that signal, so that to generate or change the response, the output. Okay. Now let me show you another one. Now it's an RC circuit. You can see 2 resistors, 1 capacitor, and a power source, and this side is ground. Okay, and you are asked to get the mathematical model of the circuit. How do you do? You first draw the currents, right? This is the voltage, and there's a current. Let us call it I1T through this resistor, and then at that point the current split into 2 sections, I2 and I3. Okay, I2 goes through this resistor, I3 goes through the capacitor, and then they combine together, goes back to the battery. Then when you want to analyze this circuit or build a mathematical model for the circuit, you need to use say Kirchhoff's current law. Kirchhoff's current law here, which says if you look at any node here, this node or this node or any other node, right, the total current come into that node is 0. Total current come into that node is 0, which means you can't have 3 currents coming into the node. Now, if you have say 1 current coming into the node, other 2 branches, you're leaving the current from that node. Okay, so total current into the node is equal to the total current going out of the node. So that is another way of describing KCL. So then if you look at this node A here, we can say I2 plus I3 is equal to I1. So this is the KCL. Now I2 means the current over here, right? That is equal to the voltage divided by the resistance. So voltage over here is VT, output voltage. Okay. This is the input voltage, this is the output voltage. So output voltage divided by R2, right? VT divided by R2. I3 is the current through the resistor, the capacitor. Current through the capacitor, you need to know the current equation of a capacitor, right? It is the capacitance times rate of change of the voltage. So I recommend you go back to your text and figure out the basic equations of a resistor, capacitor, and inductor. Okay, then you can see the current through a capacitor is C times V dot T. Okay, and the addition is equal to the current through the resistor. This one, I1. So the current through the resistor is the voltage divided by the resistance. So voltage is Vs minus V. Okay, voltage difference. Vs minus V divided by R1. Right. So after that is simple mathematical manipulation here. You can follow the process, right? And you multiply all three terms by R1 and R2 and get to this equation. Okay. And then, you know, you have a differential equation now. So V dot is the highest derivative. So you keep it as the first term. And then combine all the other V terms. V is over here, V is over here. Combine them together. And the constant term R2 times VST, you leave it on the right hand side. Now after that, if you want, you can divide the three terms by R1 and R2. Right? Then you get to this equation. And then rather than writing R1 plus R2 over R1, R2C, you combine all these things together as a constant A and this as a constant B. It's a simple equation. V dot T plus AVT is equal to BVST. So this is the mathematical model of the RC circuit. Okay. So here A is known because you know R1 and R2 and C. B is also known because you know R1. Then if you give a certain voltage to the circuit, that is Vs, right, with some Vt initially, right, initially means at time 0, if there is any voltage across the capacitor, right, that is called the initial condition, V0, you can put that here initially. Okay, now you have A, you have B, you have V0 initially, and you have the supply voltage, and immediately you can calculate the rate of change of voltage, V dot T. So the moment you understand V dot T, rate of change, you can calculate, okay, then what is the voltage after 1 second, after 2 seconds, if you go like that. The Vt is going to change from its initial value, right? So this is a dynamic process and it will change V dot T also. When V dot changes, V changes. Goes on and on and on until the circuit comes to a certain stable condition. So when it reaches that condition, the currents will not change, right? And the voltage also will not change. It will maintain at a certain value. So using the equation, we can actually see how these currents change and how the voltage changes. And if they stabilize at a different value, what is that value and how long it takes to get to that value. So I showed you two systems. One is a mechanical system, the motorcycle shock absorber. The other one is an analog circuit, electric circuit. And in both cases, what you did was you first look at the plant as a white box case, and then you identify the components and you wrote the equations of the plant, either using Newton's laws or Kirchhoff's laws, right? And then simplify the model. And in both cases, you ended up having a differential equation. In the shock absorber case, it was a second order differential equation. And in the electric circuit case, it was a first order differential equation. That is the summary. And here I have 4 bullet points as a summary. What have we learned so far? Number 1, the first bullet, system models are ordinary differential equation. Remember that. You are given a plant and you are asked to build a model for the plant. When you try to do that, you almost always end up having an ordinary differential equation. Look at over here, 2.3. And earlier, 2.2. They're both differential, ordinary differential equations. Second bullet, system complexity is represented by the model order. Yeah. So the second order model, which has a second derivative of the dependent variable, is a bit more complicated than the first order model, which has the first order derivative of the dependent variable. Third bullet, the response or output of the plant can be obtained by solving the model ODE for a given forcing function. True. If you have an ordinary differential equation which has model coefficients like A, B here, and in earlier case M, C, M, K, B, right? These are the model coefficients, right? And if you know the forcing function, here it is VST, external forcing function, and the previous case it is FT. If you know these signals, then you can calculate the rate of change of the dependent variable, right? V dot T or Y double dot T in the shock absorber, right? So there are 2 ways here. If you look at the dynamic model as an iterative thing, right? And first you calculate the rate of change or acceleration, and then update the velocity, update the position, and then go to the next cycle and so on. This is a simulation. That's a simulation. You can build a simulation. Or else you can solve the differential equation for a known signal. So once you solve the differential equation, let's say this one, this is a differential equation because there's a rate of change of the variable Vt in addition to Vt here. So it has Vt, V dot T. If you can have V double dot T like that, it's a differential equation. But when you solve it, you don't see a rate of change anymore. You only leave with Vt. Okay, Vt is equal to something, function of time. And that is what is called the solution of a differential equation. So for a known VST over here, you can solve the differential equation, which will eventually give you Vt equals what? Vt equals some function. So then you don't need to use a computer to simulate it. On paper, you can solve it. And the response, Vt, is just a mathematical expression. Okay. So being able to model a plant is very important, therefore, because then if you can solve the differential equation, you can tell what is the expected response from the plant. But it is difficult to do because solving differential equations is not that easy. And that is why we have Laplace transforms, right? We use Laplace transforms to to solve differential equations. Right. So we have 4 bullets here as the summary of the of that part. Any questions, please? There's a question in the chat. Is in the instance where the cup is not placed sort of equivalent to the instance where the cup is empty? No, that is exactly the opposite. When there is no cup, you should not let the device to flow wine, right? When there's no cup, for example, here, when there's no cup, this should close. For that, you need to have some locking mechanism here, right? You turn it this way, full, and lock it, right? The moment there's somebody who wants some wine, you put the empty cup and let it go. And once it is full, it swings back down and you take the cup out, but don't let the cross arm to go up. You keep it locked at the lower position. Any questions? Now, I mentioned that we are not going to solve differential equations manually, but we're going to use Laplace transforms. Okay. Laplace transforms is out of this course. It's not part of this course. You may have already done it, maybe at least once or maybe a few times. If you have forgotten Laplace transforms, please study it, right? Please study. And in the reference book, there's a chapter on Laplace transforms, but you can learn yourself a lot of documents on the internet. Here I also mention, not beyond anything, but this particular slide, okay, what we do. Why Laplace? Laplace is a different world. Laplace is a different world. It's not our world. It's not time, right? Our world is basically time. We measure everything on timeline, right? And differential equations are also on the timeline. They are time equations, right? Time equations. Rate of change means time. What we do is we transform time domain equations into Laplace domain. So in Laplace domain, very much like time in the time domain, what we have is a different symbol, S. So it's a transformation from Ft to Fs. Ft to Fs. Okay. So any equation in the time domain, right, can be transformed into Laplace domain, and there's a characteristic representation of any time signal in the Laplace domain. So that is what's called the forward transformation. Example, delta t. Delta t is the delta function, you know that, right? The function is 0 in the negative time, function is 0 in the positive time, but the function has infinite height at time 0. So that is delta function. Delta function. So the delta function, when you transform into Laplace domain, it's 1. It's 1. So how does this delta function becomes 1? But this one is not the time domain one. No, it is a Laplace domain one. Remember? So I mentioned Laplace is a different word. Whatever numbers in there, whatever symbols that you see there, do not try to give a meaning in time domain because it's a completely different. Okay. You need to remember though, right, that Laplace of ft delta t is 1. Take another one, unit step. Unit step is actually step like this. So it is 0 and at some point goes up and then like this. Whereas delta is something like this. Is delta. So the Laplace of ut unit step is 1 over s. And when we deal with systems, we deal with a set of functions very common, like delta, like ut, and exponential terms e to the alpha t, right? E to the alpha t or e to the at over here is 1 over s minus a. Remember the pattern, 1 over s minus a. 1 is 1, then s is s minus a. This e to the at, a comes over here. There's no time here, okay? Because this is not the time world. This is the s domain. Time is over here. Similarly, cosine function, sine function, power of time t to the n. Up to this point, these are basic functions and they are corresponding Laplace. After that, we have some operations in time domain. What are they? Linearity, right? That is superposition and multiplication by a scalar, alpha times f, then plus or minus with another time function. So in the Laplace domain, it goes like that. Alpha 1 is no change. Multipliers will remain there. And f1t has f1s. So it is a Laplace transform of f1t. And Laplace transform of f2t is over there. Sorry about this one. This has to be capital F. Okay. This is capital F. All right. And exponential scaling. This is another time function. Exponential scaling in Laplace domain, it becomes like this. F s minus a. Okay. So ft is the time function of which fs is the Laplace. ft fs. Okay, like this, ft fs. When ft undergoes this change, e to the at in front of that, this is the exponential scaling. It's a different function now. But what happens to the Laplace? Laplace changes like this. You take s out and substitute s minus a. In place of s, you write s minus a. That's it. All the places where you have s, you have to replace s by s minus a. Time shift, time multiplication. If you multiply a function ft, whose Laplace is fs, right, by time t, right, the Laplace transform of the time multiplied version would be d over ds. You differentiate fs, right, by with respect to s and put a negative sign, like that. Differentiation. You can differentiate functions in time domain like this, ft, right, dft by dt, or d square ft by dt square, second derivative, third derivative, fourth, fifth, like that. Whatever derivative, there is a corresponding expression in S domain. Okay, and remember there you can see the first one is the SNFS, this nth order derivative. Okay, so when you do that, these are all initial conditions, f0, f dash 0, and f to the n minus 1 initial condition 0. These are time functions, because simple f is time function. Okay, time function, initial values. But about integral, when if you integrate a time function, that integrated version has a Laplace transform, and it is 1 over s times fs. Time scaling like this, convolution integral is like that. The convolution integral is very important. Convolution integral is, as you know, if you remember, maybe you have done what is convolution integral or convolution sum in discrete mathematics. That is one of the most important things here in signal processing and also control systems because of this. Now let's say there is a system and there is a signal coming into the system, right? So this is the interaction between the signal and the system. Okay, there's a system and there is a signal. So when they interact each other, they produce an output. They produce an output. So if you want to calculate the output is the convolution integral of the input and the system. Now here you can see here, suppose for the moment this G is the system and this F is the signal. So there's a signal interacting with the system. So let me draw it briefly here so that you can understand. So G is the system and F is the signal, right? This is F, this is G, and then you get a output, something like that, and this is Y. So Y is the convolution integral of F and G, and this is how you calculate that. If you can work out this convolution integral, that is f tau gt minus tau d tau, right, signal and the system, and integrate it from 0 to t, what you get is yt at time t, right? If you haven't known it before, it's time to understand that. It is the convolution integral, so that is going on inside a system when it produces a response, okay, for an input signal. Now it's complicated in time domain. See here, who would want to work this out? It's like complicated, right? But if you look at the same thing in the Laplace domain, it's so easy. FSGS, my God, what has happened? Anybody can do that. FSGS, right? And also if you look at the integral here, integration also sometimes be difficult, right? But in Laplace, it's 1 over s fs. You just need to divide by s, right? It's very easy. All the operations that we usually say difficult in time domain are kind of easy in the Laplace domain. So that is why we use Laplace. Otherwise, there's no reason why we use Laplace. Because all the difficult mathematical manipulations that we do or we have to do in time domain, right? They have corresponding very simple algebraic representations in Laplace domain. That is why we like it. That is why we like it. So initially, if you get the signals from time domain to the Laplace domain, mathematical operations can be done in Laplace domain. in synthesizing the solution. And after synthesizing the solution, at the end, you can bring it back to the time domain. So that's all what I'm saying to you about Laplace transforms. I strongly recommend that you refresh yourself on Laplace transforms, right? You just need to refer to your all notes or look at some of the familiar notes on the internet. That would be good enough. Right, so at this point, I want to take a little break, about 10 minutes. After that, we'll start going again. All right. So, now we're going to look at the RC circuit model, and maybe a little later we will look at the shock absorber thing, right? How we can solve these two models, okay, using Laplace transforms. Okay, so if I just show you what we developed earlier, right, modeling, it is just this 2.3. What is 2.3? 2.3 is the mathematical description of the RC circuit. So if you give the supply voltage, right, you will not get the output voltage in this equation. In this equation, if you give the supply voltage, you will not get the output voltage, but you will get something like this. How this input signal is going to is related to the voltage and the rate of change. This relationship is there in 2.3. Okay, so if I show you the circuit, this is the supply voltage, this is the output voltage. Okay, so this equation tells you how the input is related to the output. It's a complicated relationship, and this one doesn't tell you what the output would be. Say, for example, what is V, right, as a function of something, right? So it's not there. It's not there. So therefore, equation 2.3 is only the relationship between input and output and its higher order derivatives. It is a half done thing, in other words, right? So this is what is called a mathematical model. It's a differential equation. It has input and output and its derivatives, first order, second order, third order, etc. But it is not an equation like this where we have the output V as a function of some other things. No. So therefore, we have to get it from here to here. Understand? We have to get it from 2.3 to this equation, right? So this equation is what is called the solution of the differential equation. So this one is the solution. This is the solution of the differential equation. Oops. So this one is a solution of the differential equation. If you want to get to the solution of the differential equation, right, you have to solve the differential equation. You have to solve the differential equation. In the solution, there are no derivatives any further. There is no first order derivative, there is no second order derivative, there is no third order, there are no derivatives. It is simply like this. It's simply like this. Okay, right. So now we are into that process. System response with Laplace. Let us start with the equation b dot t plus avt is equal to bvst. That is equation 2.3. The moment you look at it, please figure out that this is a differential equation. There is an input, that is vs, and there is output and its high order derivatives, vt, v dot t, v double dot, etc. Okay. And please also understand that you have to solve this in order to get rid of this v dot t and all the other high order derivatives, so that we get a solution for vt. Okay, that is what we want to know. Right, so our method is to use Laplace transforms. So what we do is, first thing is the forward Laplace transform, where we convert each and every term from time domain, this is time domain, into Laplace domain. So that is the first thing. How do you do that? We have to refer to the Laplace table, and we have to figure out whether I can find, say this one, for example, vt, right, in the Laplace domain. So let's go back to the Laplace domain. There you are. If there's a function ft, right, in the Laplace domain, we write it as capital F times s. Okay, so therefore, I think we can write this one vt as capital V times s, vs, right? So this vt is written as vs, like that. Then let's look at v dot t. So that is the differentiation, okay? First derivative of vt. Let's go back to the table. Derivative or differentiation. Here, you can see that time domain function ft, right? Once you differentiate it, what is it in the Laplace domain? So here it is the first derivative. So therefore, n equals 1 dft over dt. Okay. And on the right hand side, if n equals 1, this becomes sfs, and there's minus, right? N equals 0, 1. So 1 minus 1 is 0. S to the 0 is 1. There's no s, just f0. Are you following that process? For the first derivative, n equals 1, the Laplace is s times fs minus f0 minus initial condition. So if you look at that over here, right, you can see this is s times vs, and then this is v0, initial condition. Fine. On the right hand side, bvst. So vst in Laplace, it is, I should have changed this into a different one. But what I really mean by this V is actually the voltage, not the symbol, right? And B is over here. So what I really mean is this. So this Vs is, right, Vs is step function like this. And this value is V. That is what I really mean. So the step function, if you look at the Laplace table, there you can see the step function. Step function over here, right? Ut is 1 over s. Now, if you have the step function, unit step function, that is the height is 1, the Laplace is 1 over s. But if you have height 12 walls, 48 walls, 6 walls, this number 12, 6 or whatever has to come over here. So in our case, capital V is the voltage, supply voltage. That I know that's not the proper or very appropriate symbol, but anyway, for the moment we'll take it. So this V is that voltage, and because it's a step signal, it is 1 over s. B is the coefficient, it is anyway there. Okay, so to help you, I have written it over here for DC voltage. VST, supply voltage, is capital V times UST. This is the step signal. V is the voltage. So in Laplace, this UST becomes 1 over s. This capital V comes over here. That's the voltage, 12, 48, whatever, 6. Then the B. Okay. Now, do you see the derivatives anymore? First derivative, second, third derivative? No. Now, the moment you transform the differential equation into the Laplace domain, it is no more a differential equation. What is it then? It is an algebraic equation. Algebraic equation. Now, you learn the second thing about Laplace transforms. That Laplace transforms transform differential equations into algebraic equations. And I'm sure everybody likes algebraic equations or prefer algebraic equations to differential equations, right? It's a lot easier to deal with algebraic equations than having to deal with differential equations. That's for sure. Now, if you look at this one, this is a simple algebraic equation where you have Vs, that is the output voltage in Laplace, and then everything else is known. 1 over s is the step signal, V is the voltage, B and A are the coefficients of the system. So we combine these two terms, Vs terms here, then we get S plus A as into the bracket, Vs, and V0 goes to the right-hand side, added with the BV 1 over s. And then we isolate Vs on the left-hand side, S plus A comes to the right-hand side, 3.47. That is the Laplace equation of the voltage across the capacitor. That is the output, basically. So if I pedal back, I can show you the output voltage. That is the voltage across the capacitor. Okay. We have a algebraic equation for that now. Now, the problem is we can actually consider this as the solution. If you look at what we really want is something like this, output voltage as a function of something. So we are actually there. If you see the first term and the second term, right on the left hand side is V, output voltage. Then we have some expression on the right hand side. It looks close, right? But the problem is still we are in the Laplace domain, but we don't want the solution to be in Laplace domain. We want the solution in time domain, our domain. So therefore we have to bring them back to the time domain. And that is what is called the inverse transformation. Earlier we did forward transformation, this one, forward transformation. Now we have to do the inverse transformation. So let's take, so when we do the inverse Laplace transform, as you know, the left hand side Vs becomes Vt. right? Like that. This is the Laplace, this is the time. We have to do the same thing on the right hand side also. And if you look at the first term on the right hand side, it's 1 over s plus a v0, right? 1 over s plus a. You have to figure that out. If I see 1 over s plus a in Laplace, what is it in time domain? You have to pedal back. 1 over s plus a. There you are. It's over here. 1 over s plus a, of course, is minus a. Doesn't matter, right? In time domain, it is e to the at. E to the at. So if you adjust for this time as the symbol minus, right? What we have is s plus a. So therefore, in our case, the Laplace, inverse Laplace should be e to the minus at, right? So therefore, 1 over s plus a in time domain becomes e to the minus at, like that. Can you see that? This one, in the inverse Laplace, becomes like this, e to the minus at. So you should be able to do these things, right? Say here, this one, the forward transformation, and this one, the inverse transformation, right? So these are important things. The table, very important. You need to be a bit familiar with the table. And the second term on the right hand side, this one, b over s times s plus a. I have to figure out if there's something like this in the Laplace table, and if you go back, right, b over s times s plus a, unfortunately you cannot find anything like that, right? So therefore, let's come back to the Laplace domain and try to break it down into something like this. This is the same thing, right, in a different format. You take b over a out and break it into partial fractions, first order, right? This is 1 over s minus 1 over s plus a. And then you can go back to the table and see if you can see something like this, 1 over s. Of course, you know that's there, and 1 over s plus a. That's also there. So these two terms, 1 over s and 1 over s plus a, they are there. You can see it over here, 1 over s and 1 over s plus a. Okay, right. So for 1 over s, it is ut, step signal. In time domain, sometimes you do not write step signal as ut. You just write 1. It's a step 1. That's it. If you really don't worry about at what point in time the step signal strikes, right? Then you just can write it as 1. Okay. But mathematical symbol is ut. And 1 over s minus a, the Laplace is e to the at. Right. So now the first one, this is 1 over s in Laplace domain, right? If you see 1 over s in time domain, it is 1. In fact, it is ut, but I take 1 because I know my time start at 0. So after 0, unit step signal is 1. And 1 over s plus a, the inverse Laplace is e to the minus 80. Okay, right, fine. So now if you look at 3.49, you have V0, that is the initial voltage. If there's any voltage across the capacitor, you put it over here. And then e to the minus a t. Now time is there. Now it is in our domain, time domain. A is a coefficient based on the resistances and capacitor in the circuit, and B over A is also like that. This V is the voltage, supply voltage. It's a DC source. So whatever voltage, 6, 12, whatever, 48, you put it there. Then 1 minus e to the minus 80. So this 3.49 is very much like this. V equals a function of something. So that's the solution. Right? So in order to visualize this one, all what you need to know is substitute time. At any time, you just substitute that time, you get the voltage calculated. Okay. So this is the solution. And we use Laplace transform to solve the differential equation, this one, right? Eventually, you should be able to go from here 2.3 to 3.49. You might be wondering what these numbers are, right? 3.49, 3.47. You don't have all the numbers here, right? These are the numbers in the book, actually, right? I'm not writing every line in the book here because there was some of the intermediate equations are missing, right? So don't worry about that. So this process, getting from 2.3 to 3.49, right, involves 3 steps. The first step is forward Laplace transform. That is this one, first step, right? And then the manipulation using partial fraction or whatever it is, right? And then the last step is inverse Laplace, bringing the Laplace equation or Laplace solution back to time domain. So if you are comfortable with those 3 steps, I think you are comfortable with Laplace transforms, how to use it and how to make maximum use of it, right? So practice yourself decent time on solving ordinary differential equations using Laplace. So that will definitely help you. Any questions, please? All right. Now, let's look at another method of solving the differential equation, and this time using convolution integral. Now, as I said, we can see the problem as a signal and a system case, right? So where we have the system, right? The system is the circuit, right? System is the circuit, and signal is the voltage, that is Vs, supply voltage. So it interacts with the circuit and it produces an output, that is V, the voltage across the capacitor. And this abstract representation is very important because then we can generalize it, right? Once you generalize it, this doesn't matter whether it's a RC circuit or a shock absorber or anything else for that matter. We can treat any and all systems in the same way, okay? And the process, the interaction between the signal and the system and to generate the output is called the convolution. Now, if you treat all the signals here as continuous signals, like this, for example, continuous signals, then we call the convolution as convolution integral. But if you deal with the signals like impulse signals like that, samples coming at different levels in digital controls, right? If you are working like that kind of signals, you cannot integrate it in continuous time because now you have samples. So sample by sample, you have to do that. And we don't call it integration, we call it sum. In that case, we call it convolution sum. So convolution sum, convolution integral, depending on whether you treat your time and the signal in the continuous time or in the discrete time. We will do a comprehensive discrete time analysis in the second semester in the digital control systems. Okay. But at the end of this semester, I will tell you something about digital controls at the end of the semester. How do you convert these continuous time signals into discrete time? Right? Because nowadays we implement control systems mostly in digital domain, discrete domain, not in continuous time, right? But we cannot straight away go to discrete time because discrete time signals is difficult to handle, and there are no strong tool support. Of course, in MATLAB you have it, but if you look at the classical analytical techniques, right, you don't have as much as you have in continuous time domain for analyzing plans, designing controllers, etc. Right? So therefore, the plan and the process is we study the theory, we design the controllers, we implement them, simulate them all in continuous time, which is very familiar to us. You have been taught all this long in continuous time, so that you have a lot of experience already gathered. In addition to that, there's a lot of tools to analyze continuous time signals. So we stick to that, and discrete time is not a new thing. It is just the conversion from continuous time to discrete time. So we introduce discrete time control or digital control as an extension from the continuous time treatment. We are not going to open a whole new discussion, right, in the second semester also, right, as discrete time control. Start over again. No, there's no such thing. There's no need either. What we do is, what we have developed at the end of the course this semester in continuous time will be the foundation for the next course in discrete time, digital control. There we simply convert from continuous time to discrete time. Okay, right. So now if we consider the convolution integral, right, I use 3.47, that is this equation. Okay, this is the Laplace presentation of the solution Vs. Okay, so the first term has no problem, right, either way, but the second one we broke it into two parts using partial fractions, right? So once we did that, it was straightforward. But now what I do is I take 3.47. I do not break this into partial fractions, but I will treat this as a convolution, interaction between a signal and a system. Okay. Here, the moment you introduce partial fractions, you split the convolution into two separate entities. Therefore, you didn't have to go through the convolution. But in fact, 3.47 is a convolution. Is a convolution because it's a signal and system interaction. It's a signal and system interaction. If you look at the first term here, 1OS plus a V0, this is not a convolution. It is just one signal. Why? Because it is coming from V0. So what is V0? V0 is any remaining voltage here, initial condition. Okay, any remaining voltage here, initial condition. And it will change by its own way without anything to do with the supply voltage. So it's a self-decay kind of thing. Okay, so therefore there's no interaction here. But if you look at the voltage here, it will interact with the entire system over here and produce a voltage over here. Okay, so that is the second part. How this interaction happens. It happens like this: B over S times S plus A. Okay, so let's work that out. The second part, B over S times S plus A. Can you see two different entities here? Yes. One is this 1 plus 1 over A. Sorry, 1 over S. The other one is 1 over S plus A. Can you see the two entities in Laplace? 1 over S, 1 over S plus A. Right, so I can treat, for instance, 1 over S as my signal and 1 over S plus A as my system. So they are interacting each other. So the moment you see two entities, right, 1 over S, 1 over S plus A, two entities multiplying each other in the table, see it over here, two Laplace transforms multiplying each other. Here, two Laplace transforms multiplying each other, Fs, Gs. So what is it in time domain? Convolution integral. So all what you need to do is to figure out the inverse Laplace of f, one of the functions, and also the Laplace inverse of the other function, that is g, and put them into the convolution equation. Okay, you have to take the first Laplace transform, which is Fs, first Laplace transform, which is Fs, find out the time function, put it over here with tau, and pick up the second Laplace transform, Gs, and find out its time function, but write it as t minus tau, not just t, and then integrate from 0 to t. This is all what you have to do. Can you do that? I don't worry about the first part. It's over here. Forget about it. Take the second one. Right. I can see, right, let's say this one, 1 over S plus A. I treat this as my Fs. I treat this as my Fs. This is my Fs. Okay. So this is my Fs. Then I want to get to Ft. What is Ft? 1 over S plus A. What is Ft? 1 over S plus A. Ft is e to the at. So that is for 1 over S minus A. If I have 1 over S plus A, the time function is e to the minus at. E to the minus at. So there you are. E to the minus at. Right? So that comes over here. Then I take my second function, which is this one, 1 over S, and I take this as my function gt. This is my gt. Right? gt. But if you look at the Laplace table, I have to take gt minus tau. Gt minus tau. Right? So Now, this function gt in time domain is what? Ut, isn't it? This is ut. Look at the table. 1 over s is ut, step signal in time domain. Now, when you write it down, you have to write it like us minus tau, sorry, ut minus tau in the convolution, because you know this is convolution. Okay, that is the second function, and they are multiplying each other. And in the time domain, it is the convolution. And then you put d tau, integrate from 0 to t. Okay, so I'm not going to explain you this integration and all that. You can see that ust minus tau is anyway 1. Then it is e to the minus a tau d tau. When you integrate, it becomes like this. Okay. So once you substitute the limits and all, you get to this equation 3.5 v0 e to the minus at plus b over a vs1 minus e to the minus 8. If you look at this response and compare it with what you got earlier, 3.49, it's the same, right? 3.49 using partial fraction and 3.50 using convolution integral is the same. This is the response of the RC circuit. Any questions, please? All right. Now, as I said to you, the next thing is to simulate what you have got. So for that, I go to MATLAB, and this is the code, M code. This is the first code I want you to write yourself when you have your MATLAB installed. First thing is I declare my components in the circuit. I have 2 resistors and 1 capacitor. 2 resistors are 1 kilo ohm, 2 kilo ohm, and the capacity is 200 microfarad, picofarad. I'm not sure whether this is right. Hold on a second. I haven't done any values. That's fine. So 200 microfarad. Then A is like this, B is like that. In MATLAB, when you write, you don't have to declare your variables initially, and you don't have to specify whether they are double, float, integer, whatever. You simply can write it as you write on paper. Okay. Unless you want to convert to a certain data type, you don't have to do the typecasting up front. Okay. So V0 is the initial voltage. So we assume that there is an initial voltage here across the capacitor, right? Charged previously, and that is 2 volts. And duration is the simulation duration, and I put it to 0.6 seconds. That is about 600 milliseconds, right? And then this is how I define my timeline. From time 0 to duration, that length in time, I ask MATLAB to break it down into small slices in time, each one of 0.01 second, and that is about 10 milliseconds. So it's a 10 millisecond sample interval up to 600 milliseconds. Okay, that is my simulation timeline. Then I write what is called homogeneous response. What is that? Homogeneous response. You can see it over here. Homogeneous response. That is, if you look at the voltage, the solution of the differential equation, right? Voltage across the capacitor. It comes as two parts. The first one is the voltage remaining from the initial voltage. Initial voltage is V0. The moment you switch, close the switch, right, or connect the voltage source, you get going in your system, and there's a dynamic changes in the system, and because of that this voltage probably will die out gradually. Okay, will die out gradually. It probably will not be there. If it further charges, then of course it's a separate story, but otherwise the initial remaining voltage across the capacitor will gradually die out through the circuit. Okay, so this is how it dies out. This is how it dies out. We call it homogeneous response because it has nothing to do with the exogenous signal, that is the external signal, the voltage, the input voltage to the plant. It doesn't directly deal with that. So we give it a name homogeneous. Then we have the exogenous response, that is the voltage across the capacitor as a result of input voltage. Right, so you can clearly see here Vs over here, right? So now I have written as Vs over here to the supply voltage, right? 12 volts, 18 or whatever. So in MATLAB, I want to write this and this separately. So in my MATLAB, I figure out homogeneous response as VH, the first one, exogenous response as the second term on the right hand side. Then I combine these two together as my total response, and this is the voltage you would see had you connected an oscilloscope, right, across the capacitor. That's the total voltage. And after that, in MATLAB, maybe some of you guys who have experience in MATLAB knows about it, plotting the graphs. I want to plot the homogeneous response, exogenous response, and the total, right, in the same graph using subplot command, subplot 311. I want to partition the screen, my screen, into 3 rows and 1 column. That is why I call it this 3-1. Okay, 3-1, 3 rows, 1 column. So this is what is called 3-1-1. This is 3-1-2. This is 3-1, 3-1-3. So if I want to draw anything on 3-1-1, I have to say subplot 3-1-1. And when I say subplot 3-1-2, I'm going to draw that into the second part of the display like that. So the first one, top one, I want to plot time versus, or VH versus time. Okay, so YH, homogeneous response on the up front here, and in the middle one, exogenous response. The last one is the total response. So this is what you see if you code this and run it, right? You see the homogeneous response. You start with the 2 volts. Remember, the capacitor was charged to 2 volts initially. That is initial voltage. The moment you start get going, okay, immediately the voltage starts dropping, and around about 600 milliseconds, that whatever accumulated charge and the voltage has already gone down, died out. And this is how it happens. In the same time, there is charging from the voltage source that is connected to the circuit, energy source, that will charge the capacitor like this. Okay, the initial stored energy dissipates, but new energy comes into the capacitor, charging the capacitor. And when you add these two together, the total net voltage will look like this. Okay. Now we want to verify whether what we have done is right or not. If there's anything wrong here, right? There are ways to cross-check. So can somebody help me here to check whether what we see here, what we have derived mathematically, is probably correct or probably not correct? Can anybody check that out? Because once you code a thing in not only in MATLAB, in any simulation platform, you get nice graphs. But if the graphs doesn't matter if they're nice or so nice, but if they're not correct, there's no value in that graph. Okay, so we have to validate whether what we see here is correct. Maybe
we can substitute the time values to the equation. We can substitute the time values to the equation and check whether that value is correctly displayed on the graph.
Right. So if you go a bit further, can you tell me how to do that? What do you see here? You mentioned about final value, right?
Yes. So let's take t is equals 0.
So what is the final value here? It's like 0.6 or so, right? 7.6 or 0.7 in that area.
Yeah.
So do you think that is correct? Yeah, what you said was right, because you can you have the equation, you substitute time, a long time, right? Not only 600 milliseconds, maybe a couple of seconds, right? And then see whether it is 0. But yeah, that is you can do it that way. But what I really want you to tell me is more smart technique, right? To check. So so let's go back to the circuit. I think you are right. You are not incorrect, right? Just because you were not able to figure out the smart technique here. Now this is the circuit. This is the circuit, and if you look at the resistors that we put there, is 1 kilo ohm and 2 kilo ohms, right? So this is 1 kilo ohm, this is 2 kilo ohm. Now this is a DC source. For DC, direct current sources, the capacitor is like open circuit. You know that, no?
Yeah, yes, I know.
Yeah, capacitor for a DC source is like open circuit. Initially, there is some sort of charge going there, but after that, it becomes non-conducting element. Non-conducting element, right? So it's open circuit in the long haul. And then what you have is just two resistors and the power source. This is 1 kilo ohm, this is 2 kilo ohm. It's a potential divider circuit. Simple potential divider circuit. Whatever voltage over here will drop across the capacitors proportional to the resistance. This is 2 kilo ohm, this is 1 kilo ohm. So therefore, whatever voltage here will drop 2/3 here, 1/3 here. That's it. 2/3, 1/3. Whatever voltage that you have supplied. I think this is the step response. So therefore, this is 1 volt, right? So 1 volt, because you are taking what? Yeah, I think 1 volt signal, right? If you look at this one, VS, BVS. VS is the voltage. And there we haven't specified any VS, which means 1, okay? Which means 1 volt. So 2/3 of 1 volt should be the final value, whatever it is. So it's almost there, right? This is 1, this is 1, this is 2/3.
0.66.
Yeah. So probably this is correct. Not only the graph, I think mathematics we developed is probably correct. So why I showed you that part is that as engineers, you need to verify everything that you do. You go through the mathematical process and then you go to the simulation platform. It's not impossible that you make mistakes. Actually, you can make mistakes very often. That's all right. But what is not all right is that you don't check that and let the mistakes continue and be hidden in the process and ruining your life. So you have to check, cross-check whether what you have done is correct or not, right? Okay. So then let's look at these 3 bullets, observations and conclusions. The first one, homogeneous response, that is initial condition response, dies out, leaving no remaining response in the long run. So is that right? Go back and see. Yeah, this is the initial voltage. It dies down and takes a little while, but after that, there's nothing. So part of the solution is transient. Transient means it is there only for a brief period of time, upfront, only initially. And it can be because of the initial values here, initial charge of the capacitor. So that can that will show up for some time initially, but in the long haul, there's no effect. So that is the first bullet. Second one, exogenous response is what remains in the long run after transient time. This response finally remains as the steady state response. There you are. This part of the response is because of the voltage source that you have connected to the circuit. And it also goes through some transient initially to charge the capacitor. But around about half a second, right, it stabilizes. It is leveled. It is leveled, okay? And this entire thing is from the battery, from the DC source, right? And if you look at time from 0 to 0.5, this part is also transient response. This is also transient response. And after that, what is remaining is the steady voltage across the capacitor because of the supply voltage. And therefore, probably from here, around about somewhere here, you can say from there, this is the steady state response. Steady state response, okay? But before that, over here is transient. transient response. Okay, fine. So in order to understand the input-output relationship, homogeneous response has to be removed. There you are. Now, when we deal with systems, right, this transient response is a separate area of analysis, but more often than not, okay, what we really want to find out is the steady state response. Steady state response. Now, if I draw the plant like this, there's a system, right? And this is the input, and this is the output, right? So output goes certain changes and eventually settle there. I'm really interested in this area, not this area, right? This is not that important for me in most cases, but this is the problem where I really settle. Think about a simple air conditioner. You set the voltage to 26. Now it is 29. I really don't care how it starts from 29. It can start anyway, right? But what really matters is that it finally brings down the temperature to 26 in the room. Okay. So mathematically, it is easier to relate the steady state response, okay, and the input. We want to find out how these two are related. But if you want to analyze the transient part, right, it can make things a bit complicated, right? It can make things a bit complicated. So therefore, you will see in the next contents that we're going to discuss, we sometimes drop the transient part, or at least part of the transient response, right? That is, say, for example, this part. So maybe this part we can neglect, right? And leaving only this part. So this rectangular part we can keep, we can remove the transient part. Because you know, this signal has no effect in the long run. This is a dying thing, signal which is dying. So don't worry about it, right? After half a second, the signal is not there. So why do you keep it as an obstacle to your process? Take that out and write down a new equation where Vt is equal to this equation, this expression rather. Okay. So in that case, you can relate this Vt and this whatever Vs very clearly without this one and easily, right? All right. Any questions? Is everything clear? Oh, there's a question here. I'm using GNU Octave as an alternative to MATLAB. Unfortunately, I don't have any experience with GNU Octave. You can give it a try, right? If you can write down these codes and simulate and get what I just expected, right? So then you will be okay. you will be okay. But I have slight preference if you use MATLAB, right? But if you can do the same thing in GNU Octave, I'm okay with that either, right? So give it a try. Next week also we'll see some codes, and you can take about a month, right, to figure that out, whether you want to continue with Octave or whether you want to install your own MATLAB. All right, so today we discussed about the classical feedback control systems designed by the initial designers. And then we looked at two plants, the shock absorber and the RC circuit. So most familiar systems to many people. And then we modeled the two systems mathematically, and we figured out that we end up having differential equations when we try to model the plants. Then we figured out it's difficult to deal with differential equations. The solution we anticipate has to be an expression where we don't have any more derivatives of the variable, dependent variable or the response, so that we need to solve the differential equations, right? So for that we use Laplace table, and of course you need to brush up yourself about Laplace transforms, right? Solve some problems that you probably solved many years ago, bring it to the front. Then the other thing is we looked at the response coming out of a plant as convolution integral between a signal and a system, okay? The interaction. And also we look at how Laplace transforms can be used to solve or manipulate mathematical equations, differential, as algebraic equations, right? And then how to bring the Laplace solution, right, to time domain using inverse Laplace, okay? And then we looked at how we can use MATLAB to simply code it, our responses, and then look at it ourselves and see whether this is probably right or wrong. And we also cross-checked whether what we see on screen is right or wrong, right? So that's quite a important process that you walk through today. You should not miss any of these things, because this is a standard procedure. First the mathematical modeling, and then solving the equations, right, to get to the solution, and then simulate and then verify. So after that, what comes is implementation in using real hardware, right? Right. So that's about for today. If you do not have any questions, I would like to wind up today's session here. Right, looks like everybody's happy and confident. In that case, I'm going to wind it up today. I'll see you next week. Have a good evening.
Good evening, sir. Thank you.
Yes, good evening, sir.
Thank you, sir.
Thank you, sir.
Thank you.